So first of all, we would just like to wrap up our discussion on temperature dependent transport properties. So we were looking at electrical conductivity and thermal conductivity, and we saw that for electrical conductivity, the most efficient mechanism for thermal relaxation comprised of momentum transferal kicks, that is horizontal processes in which these electrons on the right side of the Fermi sphere can be catapulted in to the holes on the left side of the Fermi sphere. So this is the most efficient mechanism for thermal conductivity, electrical conductivity. And थोड़ी सी आवाज़ आहिस्ते वो तेज़ कर थोड़ी सी. So this really means that what is required is that if an electron has an initial wave vector k1 and a final wave vector k2, then the two must be related by the momentum of a phonon. So if this is an initial wave vector for an electron on the right side of the Fermi sphere, after absorption of a phonon whose wave vector is this long, one would obtain an electron with a wave vector k2 which is on the opposite side of the Fermi sphere. So such a long wavelength is required. A long wave vector for the phonon is required. So this can only happen when the phonons have a wave vector of the order of q, which is the difference of k2 and k1. And this q is long enough that it spans from the right side of the Fermi sphere to the left side of the Fermi sphere. And corresponding to each vector of the phonon, there is a particular energy. So this is the mechanism for electrical conductivity. For thermal conductivity, on the other hand, you will have this smearing and anti-smearing of the Fermi-Dirac distribution. So one would have excess electrons on the right side of the Fermi sphere, excess electrons here, and excess holes on the inner side of the Fermi sphere and on the exterior of the Fermi sphere here. So two kinds of mechanisms can take place for thermal relaxation. One is the conventional horizontal process in which a change in wave vector for the electron is so large that it can take an electron from one side of the Fermi sphere to the other side. But in addition to these processes, you can also have vertical processes in which an electron just falls into a hole that is nearby on the same side of the Fermi sphere. So you could have these two kinds of horizontal and vertical processes for thermal relaxation. Now let's see which of these processes really happens. And of course, the phonons have an energy of the order of kBt. So what we would really like to see is at what temperatures do the phonons have sufficient energy that this cross country, this cross Fermi sphere translation of the electron can take place. So if you consider temperatures that are larger or of the order of the Fermi of the Debye temperature. Now solids have a Debye temperature which is of the order of room temperature and its whereabouts. So if an object is at room temperature, a metal is at room temperature or temperatures slightly larger than room temperature of the same order of the Debye temperature, and I'll show you a plot of the Debye temperatures for different solids in shortly in this class. So what happens in this case? In this case, we do know that the maximum temperature phonons can have inside a solid is roughly equal to the Debye temperature. That's the cutoff frequency for phonons. And the temperature corresponding to the Debye frequency omega d is theta d. So at large temperatures, such as the room temperature, phonons have a temperature theta d which is of the same order as the ambient temperature. So when the temperature is large, then that temperature is of the same order of magnitude as theta d. Okay? And the maximum temperature that an electron can have on the Fermi sphere is also Tf. So what this means is that at large temperatures, the Debye temperature and the Fermi temperature, they are of the same order of magnitude, they are comparable. And both of them, so what does this mean? This really means, okay, so let me just backtrack a little bit. Large temperatures, the Debye temperature and the temperature are comparable. Now for a phonon which has a temperature theta d or a frequency omega d, the wavelength of such a phonon is equal, roughly equal to the length of the reciprocal lattice vector, or it's the reciprocal of the unit cell spacing. So if A is the unit cell spacing, then 2 pi over A is the length of the reciprocal lattice vector, and this would be the wavelength of the phonon. This is how the Debye frequency is defined. The Debye frequency is such that phonons with the frequency equal to the Debye frequency have an effective wavelength that is comparable to the length of the reciprocal lattice vector. Okay? Now, in a Brillouin zone, this is the outer edge of the first Brillouin zone. And it must be comparable, therefore, to the Fermi wave vector. Right? So if the Fermi sphere extends to the outer edges of the first Brillouin zone, which it normally does, then the wavelength of the phonon would roughly match 1 over the wave vector, the Fermi wave vector. Okay? Or lambda f. So lambda phonon would be the same as lambda f, which means that kf would roughly be the same as the Debye wave vector. Now when this is true, so if you observe, an electron at the outer edge of the Fermi sphere has a wave vector k1, which is roughly the same as the Fermi wave vector. These magnitudes are the same. K2, which is the final wave vector for the electron after relaxation, which is on the other side of the Fermi sphere, has a wave vector K2. and its magnitude is also the same as the Fermi wave vector. Okay, so if you look at this geometry, this wave vector q should also roughly be the same as kf. Suppose this is an equilateral triangle. So if phonons of this wave vector q comparable to the Fermi wave vector are available, then this process is an efficient process. This process will happen. Now at large temperatures, we do know that q, which is nothing but kd, q is the wave vector of the phonon, which is roughly comparable to the wave vector, the Debye wave vector, which is comparable to the Fermi wave vector. All three are the same. So this process can happen easily with felicity at high temperatures. So this process does happen. Okay, so at high temperatures, this is an efficient process. As far as thermal conductivity is concerned, at high temperatures, you can still have these backscattering processes because phonons are available at this temperature. Phonons with such a large length are already available. So you can have these momentum reversal processes. So the same kind of process determines thermal conductivity and electrical conductivity at high temperatures. And the two scattering rates turn out to be the same. Therefore, the tau sigma and tau k turn out to be the same, and L equals the nominal value for the Lorentz number. L is the same as L naught. So this is what happens at large temperatures. Yes? Explain what? तो पूरा पिछले 10 मिनट यही है. So what is needed? So for electrical conductivity, you need to take electrons from the right side of the Fermi sphere to the left side, which means an initial electron wave vector is pointing to the right, final wave vector is pointing to the left. So the change in momentum, which corresponds to the absorption or emission of a phonon, must be this long. So its wave vector must be comparable to the Fermi wave vectors. At large temperatures, close to the Debye temperature, this wave number or wavelength for phonons is indeed available. So this process is highly efficient. It does take place with equal facility as the process for which thermal conductivity takes place. Thermal conductivity, by the way, takes place both through horizontal and vertical processes. So this process from going from right to left of the Fermi sphere is equally facilitated or sped up at high temperatures. Both of them are equally facilitated. Therefore, the scattering times for thermal and electrical conductivity are the same at high temperature. Now, if you look at the formulas for electrical conductivity rho we've seen is proportional to 1 over tau sigma. All right. Now, this scattering depends upon the number of phonons that are available at temperature T. And the phonons, of course, have the correct wavelength to enable this momentum reversal process. So this tau will be inversely proportional to the number of phonons, because higher the number of phonons that are available of the correct energy, of the correct wave number, of the correct wavelength, higher the number of those phonons, smaller will be the scattering rate. So rho is proportional to the number of phonons that are available, right? And in yesterday's lecture, we observed that the number of phonons at high temperature is proportional to the temperature. So the electrical resistivity at high temperatures, temperatures of this kind, is proportional to the temperature. So you increase the temperature, the resistivity goes up for a metal. As far as the thermal conductivity is concerned, if you observe the formula for thermal conductivity, can you speak up the formula for the thermal conductivity which has the temperature and the scattering time? Can you check your notes? It's basically the prediction is 1/6 pi square n kb square EF Vf square, all of these are constants, temperature into tau kappa. Okay? So this is the formula that we have for thermal conductivity. All of this is a constant here. Now, if you observe, there's a product between the temperature and tau kappa. Tau kappa is the scattering due to the phonons that are available that can affect this relaxation process. Now, this tau is again proportional, inversely proportional to the number of phonons that are available. And we know that those phonons have the correct wave number and the correct energy, so all of them will contribute to the relaxation process. So overall, this is proportional to the temperature multiplied by 1 over the number of phonons. Correct? Because tau is proportional to 1 of the number of phonons. Higher the number of phonons, smaller the scattering time. Now the number of phonons at high temperatures is proportional to temperature. So the conductivity turns out to be independent of temperature. The thermal conductivity is independent of temperature at large temperatures. So even though the electrical conductivity goes up, this transport property is dependent on temperature, varies linearly. The thermal conductivity kind of plateaus off at large temperatures. Now in the small temperature regime, at the other extreme, or not too small temperatures. So what we have is, so for the case when T is less than the Debye temperature. Now phonons will not be available because the typical energy of a phonon is kBt. When phonons have this much energy, their wave vector also changes. Correct? So at these low temperatures, what's going to happen is that omega is much smaller than omega d, which means that the wavelength is larger than lambda d, the Debye wavelength, which means that Q is much smaller than kappa d or kappa or kf, kd or kf. So the wave number of the phonon, or the length of the momentum of the phonon, the momentum vector of the phonon is much smaller. You do not have the luxury of these long wavelength phonons in the system to affect this transition from the right to the left side of the Fermi sphere. Therefore, the electrical conductivity kind of goes up, which means that the scattering rate goes longer, becomes longer, which means the the electrical conductivity is increased and the resistivity drops. It takes more time for an electron to go from the right to the left side. One kick of one phonon absorption emission process cannot affect, it does not have that much wave number or that much efficiency to affect this transition from the right to the left side of the Fermi sphere. So one kick is not enough, you need many kicks. Okay, so it becomes a highly inefficient process. And if you look at the Fermi sphere, the picture in the Fermi sphere for these low temperatures, as far as electrical conductivity is concerned, you have an initial electron wave vector, and your phonon wave vectors, they are small. So they don't make the electrons go from one side of the Fermi sphere to the other. They kind of just turn them around. So many kicks, many phonon absorption emission processes will eventually, large number of them, exceptionally large number of them will eventually turn this wave vector for the electron from the right to the left side of this Fermi sphere. And hence electrical conductivity becomes higher, or electrical resistivity is smaller. More time is needed. Tau sigma goes long, which means the conductivity gets better. So that's why this tau sigma is now longer than tau kappa. And since L has tau kappa over tau sigma, this L becomes smaller than the Lorentz number at the nominal value of the Lorentz number. Yes. देखो ये जो k वेक्टर है ना, इसे यहाँ से यहाँ जाना, लेकिन उसको मुश्किल पेश आ रही है. उसकी स्कैटरिंग प्रोसेसेस कम हो रहे हैं in order to relaxation get slower. So in between scattering processes, the time for which that electron survives with its native wave vector is longer. Tau sigma therefore is longer now than tau kappa. Higher this scattering time, smaller the mean free path, slower will be the decay. Okay, so this is what happens at low temperatures. And if I look at this, if this angle here is theta, I can actually calculate how efficient is a process in turning around this k vector from the right to the left side. So the efficiency of this process, really for an efficient process you want theta to be 180 degrees so that you can get a transition from this side of the Fermi sphere to the other side. But now this theta is much less than 180 degrees. So there is an efficiency compromise on this scattering process, and we can calculate this efficiency compromise. Any questions? I mean, it's complicated, isn't it? But I'm trying to kind of make it systematic. I'm trying to use as much as English as I do know. Of this process. So let's make a diagram. This is my initial wave vector for electron K1. Okay. Now, suppose a phonon is absorbed, Q, of wave vector Q. The new wave vector for the electron is K2. So this is theta. We do know that this K1, its magnitude is the same as Kf, because we're talking about electrons on the Fermi sphere. Only those are to be scattered, because only those can be scattered, because everything is jam-packed inside the Fermi sphere. We know that this K2 is also the same as Kf. They just point in slightly different directions. There's a small angle theta in between, because this Q is small. This Q is small because the temperature is small, as I've described over here. Now, what is the change in momentum of an electron through, for example, the absorption of a phonon? So this was the initial momentum. The amount by which the momentum changes of this electron is just this much, right? Delta K. This is the change in the momentum of the electron. K, I'm representing the wave vector for the electron, and Q for the photon. So this is the loss in momentum of the electron. you really need a large loss. You need a loss of minus 2k for this Fermi vector to flip its direction altogether. You need a loss of minus 2k. But here you have a very small loss delta k, which of course depends upon the small angle theta. So how much is this delta k? This delta k, if you look at the geometry, is simply this length, which is kf, minus this length, which is kf cosine theta. So this is kf 1 minus cosine theta, isn't it? Now this 1 minus cosine theta, this I think is 2 sine square theta over 2. Correct? 1 minus cosine theta is sine square theta over 2. Okay, or another thing what we could do is this kf, let me write this cosine theta, since theta is small, let me write this as 1 minus theta square over 2. So this becomes kf theta square over 2. This is the change in momentum. So this delta k is much smaller than kf, which means theta is really small. So this is the maximum change in momentum. All right. Now I can also express this in terms of the momentum of the phonon. If I look at this large triangle over here, I do know from the cosine law that this q square, length q square is kf square, this kf square plus this kf square, 2kf square minus 2 kf square cosine theta, right? This is the cosine law applied to this pink triangle. So this becomes 2kf square 1 minus cosine theta, which is again theta square over 2. This means theta square over 2 can be written as q square over 2kf square. Now I take this in here, this becomes kf q square over 2kf square, which is q square over 2kf. So the change in momentum for a single scattering event for the electron at low temperatures is h bar times delta k. So one scattering event of an electron with a phonon affects a change in momentum which is given by h bar delta k, which is h bar q square over 2kf. Now we also know that if you look at acoustic phonons, we also have the relationship that for acoustic phonons, omega is the speed of the phonons into q, correct? So this q square becomes proportional to omega square. So therefore the loss in momentum for an electron in a scattering event becomes h bar square omega square 2 kf speed of sound squared. All right. So what does this mean? This means that Yes. So what does this mean? So what's the relationship? What is h bar omega? What is h bar omega for a phonon? That's the energy of a phonon. Correct? So this is the energy of a phonon, h bar omega squared. Now what's the typical energy of a phonon at a temperature T? Yesterday's lecture, what's the typical energy of a phonon at temperature T? kBT. Right? The typical energy scale of a phonon at temperature T is kBT. So now you're going to take the square of that energy. This factor has to be proportional to the square of kBT, which is proportional to T squared. So the loss in momentum for a single scattering event is of the order of T squared. Now if you look at the time for scattering that contributes to electrical conductivity, we do know that this, if the temperature is higher, this temperature is higher, there will be a greater loss in momentum, which is what we need for relaxation. So this tau will be inversely proportional to the square of temperature. Right? So higher this temperature, higher will be the change in momentum, more efficient will the process of relaxation be, because you want a change in momentum for electrical relaxation. So the time would be therefore inversely proportional to delta P, to the change in momentum. If delta P is large, then the scattering rate will be large. The time required for scattering will be small. So this is inversely proportional to delta P. And you also need to consider the number of phonons in the system. Correct? So higher the number of phonons, smaller will be the scattering rate. So not only do we have a factor of delta P, which really demarcates the efficiency of this scattering process, you will also have a number of phonon factor inside the denominator. Higher the number of phonons, smaller will be tau. So this term we already had when we considered. So this is the same thing as I've written over here. This term was already there. This term was already there. The additional scaling factor due to the smallness of the temperature, due to the inefficiency of the scattering process, contributes this delta P. Now this delta P is proportional to T square. So this becomes 1 over, this is proportional to T square. And what about the number of phonons at low temperature? At low temperature, the number of phonons is proportional to the cube of temperature, isn't it? So we have a factor of 3 here. So this tau is proportional to T raised to power minus 5, which means that the electrical resistivity, which is N E square, which is M over N E square tau sigma, is now proportional to the 5th power of the temperature. So at high temperatures, the electrical resistivity is proportional to the 1st power of temperature, and at low temperatures, this electrical resistivity is proportional to the 5th power of temperatures. And what about the thermal conductivity? The thermal conductivity does not need this long scattering event. Thermal conductivity can take place by the drama that is happening at the Fermi sphere, through these vertical processes. So this kappa, which depends upon the product of temperature and tau kappa is such that this depends upon tau, and this tau k mainly depends upon the number of phonons in the system. Right? And the number of phonons in the system is proportional to tau cube. So this depends upon T over T cube, which depends upon T to the power minus tau. So the conductivity, the thermal conductivity at low temperatures would now be proportional to 1 over T square. So let's make a plot of this and see what's happening. So if I were to draw the temperature here and the electrical conductivity, I know that at large temperatures, rho is proportional to the temperature. At intermediate or low temperatures, so here we have scattering due to phonons. Here we do not have enough phonons for this back scattering of the Fermi wave vectors for the electrons. So we have inefficient processes. Therefore, we've already indicated that in this regime, the temperature now, the resistivity now varies as the fifth power of T, or ideally it should, at least theoretically. So this is a curve for the ideal resistivity. Our scattering mechanism gives us a relationship of this kind, solely describable by electron-phonon interactions. And what happens in practice is that at really low temperatures, say close to a few kelvins, this electrical resistivity just becomes constant. At some value, this intrinsic value, non-zero value, to which this electrical resistivity settles down, let's call it rho naught. This rho naught is due to impurities inside the system, ionic impurities in the system. You cannot make a pure substance, so there will always be impurities. And those impurities can be of different kinds. So you can have an ionic lattice. Say, if you're looking at copper, you could have a copper atom, one copper ion replaced by a zinc ion, or one copper ion replaced by, say, a nickel ion. So you can have these impurities. So those impurities are scatterers for the electrons. So you've understood in your previous classes what Rutherford scattering is. Rutherford scattering is that an electron or a subatomic particle is seeing a nucleus or an ion, and it gets scattered at various angles, sometimes at very large angles. So now you have exactly the same thing, an electron and a nucleus and an electron cloud around that nucleus. You have a Rutherford scattering event. So these ions have the resistivity settle down at some basal value. Okay, so overall the resistance kind of tries to have a shape of this kind. And you could also say that the resistivity is m over n e square tau due to phonons, which is temperature dependent, which describes this part of the graph, plus some intrinsic resistivity due to impurities. So this is what generally the resistivity plot looks like. And if we make a plot of the thermal conductivity, constant value for kappa. This is constant. Then at intermediate or low temperatures, you have this 1 over T square dependence. So you get an increase. But then your impurities kick in and you have a kappa that is proportional to temperature. So this is the general curve for the thermal conductivity. All right, any questions? It's a slightly complicated argument, it's a long drawn out argument, but it's totally explainable in terms of the electron phonon collisions. Now the problem is that as far as the electrical resistivity is concerned, even if you had a pure metal, by the way, one question, if I have a metal and at low temperature, so this is the temperature, at low temperature you have the resistivity plateau off at a certain value. If I have a purer sample, what will this curve look like? Resistivity versus temperature. You have a purer sample. So the curve will look something like this. Okay, so purer samples lead you to resistivities of this kind. Now the problem is that you hardly see this raised to power 5 dependence of the temperature on the resistivity. Now there could be different reasons for this. First of all, we've only assumed that electron phonon interactions are causing electrical resistivity. And we have neglected in a sense electron collisions. Because we've already mandated that electrons do not interact with electrons. These are free electrons. They're not interacting with other electrons. But in most cases, that's a very good approximation, as I'm going to describe in a minute. Electron collisions have a very little impact. But sometimes they do. There are other reasons why this T raised to power 5 dependence does not manifest itself. For example, one reason is that the Fermi sphere generally is not a perfect sphere. The Fermi volume for electrons inside metals takes this very complex shape. I'll probably show some of these shapes tomorrow. Another reason could be this process called Ohm-Clap scattering. Now here you observe that a phonon has a short wave vector. It does not have a long enough wave vector to cause this electron wave vector to flip from one side to the other. But this entire picture is drawn inside one Brillouin zone. This Fermi sphere is in one Brillouin zone. But the reciprocal space picture is periodic. So you have the first Brillouin zone, this K structure, this K sphere is then replicated, it's periodic. We know that the reciprocal space is periodic. So if I draw two Brillouin zones, neighboring Brillouin zones, suppose this is my first Brillouin zone, the second Brillouin zone, this is the K, I'm drawing everything in the K space, and suppose I have a Fermi volume inside the first Brillouin zone. Now I'm not drawing a sphere, I'm drawing some arbitrary shape. And then I have a Fermi volume which repeats itself in the second Brillouin zone. Now it's possible that I have an electron wave vector which is equal to the Fermi wave vector K1. Now phonons are not available, the temperature is low, phonons are not available so that a transition from K1 to the other side of the Fermi vector, Fermi sphere can take place. However, small wave vector phonons are still available. So you can have a phonon with a small wavelength q that takes this electron to a neighboring Brillouin zone, and still you remain at the Fermi sphere, at the Fermi boundary. So what this scattering process is doing is that a phonon of small wave vector is still available, and it is transporting the electron from one Brillouin zone to the next Brillouin zone because of the periodicity in the reciprocal space. Now this point, so if this point is A, this point is B. This point B, this point B is totally equivalent to a point C inside the first Brillouin zone, where this is a reciprocal lattice vector. So I can move inside the K space and change my position by reciprocal lattice vectors and still arrive at the same point. So this point B is totally equivalent to the point C. It's related, both of them are invariant points. So what is happening here is, through a scattering process of this kind, albeit with a small wave vector phonon, you can achieve a switch, a flip of the wave vector of the electron. This scattering process is called Umklapp scattering. So you can have Umklapp scattering, and this kind of breaks down the T⁵ dependence. Now another question I would like to ask you, okay, all of this is kind of these are very sophisticated arguments, but as we are in the twilight of this course, we need to kind of at least get introduced to these sophisticated arguments. Now what about electron-electron scattering? So when two electrons interact with one another, can they cause resistivity, electrical and thermal resistivity? Yes, okay, let's see. So first of all, if I were to, let's look at the possibility of electron-electron scattering. So if I were to draw the Feynman diagram for electron-electron scattering, so electron wave vector k1, electron wave vector k2, they interact with one another and they produce a wave vector k3 and a wave vector k4. So momentum and energies have to be conserved. So we do know that k1 plus k2 must yield the same sum for the wave vectors, and the energies must be the same. It's an elastic scattering process. No phonon is involved. So we know that these two relationships must hold. Now suppose, let's look at the easy problem. Is electron-electron scattering happening at 0 kelvins? Let's see this problem. At 0 kelvins, the Fermi sphere is totally occupied up till the boundary of the Fermi sphere. Okay? So if I draw the Fermi sphere at 0 kelvins, this is the Fermi sphere, it's totally occupied, it's filled right to the brim, and there's no spillover. So now you take two electrons inside the system, both of them must lie inside the Fermi sphere. Suppose those electrons are here inside the Fermi sphere, close to the boundary of the Fermi sphere. Electron 1 and electron 2. Now if a scattering event were to take place, after scattering, these electrons K3 and K4 cannot go inside the Fermi sphere because the Fermi sphere is already filled. So they have to go outside. So if one of the electrons goes outside, 3, and you want to conserve, say, the energies you know are proportional to the square of the distance from the center of the Fermi sphere, because the free electrons, they are proportional to k square in a sense. So if a fourth electron has to be created, if you want to conserve this or satisfy this constraint, that fourth electron must have an energy, must be inside the Fermi sphere. Otherwise you won't be able to conserve energies. But nothing can be created inside the Fermi sphere because the parking lot is already full. So a fourth electron cannot be created, which means electron-electron scattering cannot take place at 0 Kelvin. It's forbidden. Okay? So electron-electron scattering is out of the question at 0 Kelvins because of the Fermi-Dirac statistics of the Pauli exclusion principle. Now at slightly higher temperatures, say temperatures above 0 Kelvins, is electron-electron scattering possible? Yes, it is, but with a very small efficiency. Now let me draw this. So if I draw this in my Fermi sphere, suppose I have one electron inside and one electron outside the Fermi sphere. Okay? So I can have electrons outside the Fermi sphere because I can have electrons in this band of width kBt because I'm at slightly higher temperatures. So I can have an electron here, okay? So I have these two electrons and they interact with one another and they create two new electrons, supposedly energies E3 and E4. Now those two electrons have to be kind of created. They cannot be created arbitrarily in any region of space whatsoever. Those electrons have to be created outside the Fermi sphere, because inside the Fermi sphere it's almost packed, and this we've seen that this kind of spreading is very small. T over Tf is of the order of 10 to the power minus 5. This band width is really much smaller than the Fermi temperature. Fermi temperature is very large, thousands, tens of thousands of kelvins. So nothing can be created inside. Suppose two electrons are created somewhere here, 3 and 4. Now if I were to satisfy this constraint and I take the Fermi sphere, this surface, as energy E equals 0, suppose the electrons outside have positive energy and the electrons inside have negative energy. Okay, so if I look at this expression over here, E1 plus E2 is E3 plus E4. Now this is positive, 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 and the sum of course is positive. E2 is positive. Now E1 is negative. So E2 plus, so this really turns out to be E2 minus E1. Correct? Equals E3 plus E4. Now if I change this a little bit, so E2 minus E3 plus E4 equal to E1. So what does this mean? This means that E1, the magnitude of E1, which tells us how far is E1 from the Fermi sphere. This magnitude is how far inside the Fermi sphere is this electron. So this magnitude is E1 modulus. So this modulus, E3 and E4 are some fixed values, which means that this object has to be within a certain range. E3 and E4, depending upon the relative sizes of E2, E3 and E4, this object has to satisfy this constraint. E1, this distance cannot be very large. Why cannot this be large? Because E2 is just some number kbt of the order of kbt. This is one number of the order. E3 and E4 cannot go beyond E2, because otherwise this condition will not be fulfilled. So this E1 has to be within a narrow band. In other words, if I were to put E3 and E4 as 0, this E1 has to be the maximum value E1 can take. What's the maximum value E1 can take? E2. But it's generally smaller than E2. So E1 maximum is when E3 and E4 are 0. And they're very close to the Fermi sphere. So the maximum value this can take is E2. Which means that the maximum distance E1 can be from the Fermi sphere is determined by how far is the other interacting electron from the Fermi sphere. So if I were to draw a circle which passes through E2, and it is outside the Fermi sphere, then this E1, this is a certain size of the circle, this E1 has to be inside a circle which is of the same width as this E1. It cannot be further down inside the Fermi sphere. So if electron scattering were to take place, and if you wanted to satisfy this constraint over here, then this second electron cannot, there's a narrow range within which the two electrons can lie. And this range is of the order of T, kBt. So this constraint kind of gives a temperature dependence on two electron scattering, which is of the order of T. So everything lies within this narrow range of width kBt inside the energy diagram. So electron scattering does take place, and it looks like it's proportional to the temperature T. Okay, but what about this constraint? This is another constraint. We haven't considered this constraint. The k vectors are interlocked as well, because the momentum has to be conserved. So this Newtonian principle of momentum conservation kind of has its impact at the microscopic scale when we're talking about electrons as well. So if I were to make a zoomed in view of, this is my Fermi sphere, this is my Fermi sphere. So what I could do, suppose I have an electron here, number 2, electron here, number 1. So the geometrical construction that one needs to build so that this constraint is satisfied, and I'm just stating the result here. I don't want to go into the derivation, it really takes a lot of time and it's a subtle argument besides the point, is that if I draw a circle, which passes through these points 1 and 2, and I connect these points, so this is the diameter of circle, then points 3 and 4 must lie on diametrically opposite sides of this circle. Only then will K1 plus K2 equal K3 plus K4. So K3 and K4 have to lie in this regime as well. So everything is locked. So this gives a factor of T and this gives a factor of T. So both of them together, if electron scattering were at play, at low temperatures, the dependence of the resistivity will depend upon the square of temperature. And this is what is actually observed for most metals. But there are other subtle effects as well. One effect is called the phonon drag. Phonon drag. A phonon drag means that an electron, when it is drifting and is causing conduction, it drags phonons with it. Phonons are quasi-particles and they kind of move together like a sticky adhesive. They stick together to the electrons and the phonons move together with the electrons. Now I'm going to show you some real plots of resistivities and thermal diagram here. So what I've done here is, this is a very interesting table. What I've done here is, these are different metals, okay, starting from copper, silver, gold, etc. Their electrical conductivity is, all of them is of the same order, 10⁻⁷ in these units. I think these units are per ohm per meter. Siemens is per ohm, I think. The carrier density for all of them is of the order of 10⁻⁴ per cubic meter for all of them. Okay. The Lorentz number at room temperature is, as we've seen that at room temperature, the Lorentz number turns out to be this value. At large temperatures, we've seen that the Lorentz number approaches L0. At low temperatures, it deviates. So at large temperatures, this is the value for the Lorentz number. The Fermi energies for all of these electrons, as you can see, ranges from 2-3 electron volts to 10 electron volts and so on. Okay, and the one interesting observation is that the Hall coefficient shows two kinds of behaviors. First of all, it's not, there are 1 or 2 orders of magnitude deviation in their values. And the second point is that some are positive, some are negative. Which means even though these electrons have, these metals have electrons as their charge carriers, generally that's what is believed. In some cases, the Hall coefficient switches sign, which means that the nature of charge carriers is different from electrons. They're not electrons, rather they're positive charge carriers called holes. Holes are the main source of conductivity. So experiments actually give us all of these values. And if I were to kind of show you the Debye temperatures for these solids, theta D. So the Debye temperatures for these metals is roughly between 100 Kelvin and 700, 800 Kelvin or 1000 Kelvin. So all of the Debye temperatures are within this range. of the order of room temperature. And that was my original claim when I was building the argument for what's happening at high temperature. The Debye temperature, which tells you what the cutoff frequency is, what is the shortest wavelength possible in order to invoke the continuum model for the solid, in which we do not look at the quantumness or periodicity of the atomic structure. That's the temperature called the Debye temperature. So all of these Debye temperatures are inside this regime of between 100 and 700 or 800 kelvins. Okay? And this Debye temperature is a characteristic of the solid. And it's empirically determined. So you do a heat capacity versus temperature plot, and from a fit of that plot you determine the Debye temperature. And then you look at, so this is a very interesting graph. It's taken from this book. In this graph, what the authors have done is taken 4 metals, gold, sodium, copper and aluminum, and these are the Debye temperatures for these solids. And they've plotted all of them. So the temperature has been normalized with respect to the Debye temperature, and it's been normalized with respect to the maximum resistivity for any of these metals. And all of these elements show a temperature dependent resistivity which lies on the same graph. And this is, so all of these metals behave almost identically as far as resistance versus temperature is concerned. Right? So in the next graph, here are plots of the thermal conductivity with respect to temperature. It plateaus off, then it goes as 1 over T square, and then it drops down due to the impurities. Now at low temperatures, we do not generally see the T⁵ dependence. So electron scattering does play some role at low temperatures. Even though it's totally blocked at 0 kelvins, it does play a small role at low temperatures. And the temperature dependence, of course, has to be proportional to T square. So if you plot the log of the resistivity versus the temperature, there should be a line that has a slope of 2 because of the T square relationship. Now these dashed lines are the, so this is nickel, this is cobalt, this is niobium, palladium. So for these metals, the relationship, so let's look at this graph. So this solid line shows the T² dependence, and this dashed line shows a dependence or T⁵3.1 instead of T⁵2. So these asymptote towards a T² dependence at low temperatures. So it's not exactly T², it's slightly different from T², but of the same order. So this is because of electron interactions. Now some other graphs I would like to show you is, if I were to plot the resistance versus the inverse of the magnetic field, you get these oscillations. Not only do you see oscillations in the magnetization, you also see oscillations in the resistance in the presence of magnetic field. So these are oscillations in the magnetoresistance. These kinds of oscillations are called Shubnikov-de Haas oscillations, and these are due to Landau quantization. Because now the density of states is no longer a continuum, it has these spikes, and whenever a spike crosses the Fermi sphere, you get a sudden change in the resistivity. So these are the Shubnikov-de Haas oscillations. You can also look at these oscillations inside the frequency domain. These are the kinds of oscillations, de Haas oscillations. The oscillations inside the magnetization of the medium with respect to omega c, with respect to 1 over b, which is 1 over omega c. Okay? So, in a particular two-dimensional metal, these are what the oscillations look like. And these are, as you know, an impact of the Landau quantization effect. So in tomorrow's class, what we're going to do is we're going to do